In this video, I'm going to prove the properties of the dot product. If u, v, and w are any vectors in Rn, and c is a scalar, then we have these four properties over here. Let's go and prove them. The proof of A. Well, A actually has two parts. I need to prove this, and then I need to prove this if and only if statement. So why don't we call this A1? The proof of A1. So I want to show that u dot u is positive whenever u is not 0. So we assume that u is not the 0 vector. That is, u does not equal to the vector that has all zeros. Okay, so u is equal to u1, u2, all those n entries, u1, u2, u3 up to un, they are real numbers. u1 is a real number, u2 is a real number, etc. Well, this would imply that u dotted with itself would be u1, u2, all the way down to u sub n dotted with u1, u2, all the way down to u sub n. And this is going to be u1 times u1, which is u1 squared, plus u2 times u2, which is u2 squared, all the way down to plus un squared. Now, each of these entries are at least 0. You can square a number and get a negative. You can get 0, just square 0. You can get any positive number by squaring the square root of that positive number. Well, what do you square to get 13.1? Answer, the square root of 13.1. Okay. Now, since u is not 0, that is our assumption, that implies that for some u sub I is not 0. Maybe instead of saying u sub I, I'll say for some I, u sub I is not 0. Well, that will imply that u sub I squared will be positive. Now, if this number is 0 or positive, and that number is 0 or positive, and that number is 0 or positive, the sum can be 0. But one of these is positive. So if you have 0 or positive, plus 0 or positive, plus positive, plus 0 or positive, plus 0 or positive, plus 0 or positive, you'll be positive. That is, this sum will be positive. But this sum is u dot u. So u dot u will be positive. So I have what's in green, which is now in red. I have this. Now, let us look at this one here. This has to be proven in two directions. Let's look at those carefully. The first one will be that u dot u equals 0 implies that vector u is the 0 vector. But you know what? Let's look at the contra. Let me write down the other one as well, but let me put it a little bit lower. Going in the other direction, we have to show that if u is the 0 vector, that implies that u dot u is 0. Okay, now if we look at this one more closely, the contrapositive, that means I negate this. I say that u is not the 0 vector, implies not this. U dot u is not 0. But that's just what I did over here. This is exactly what I proved over here. If u is not 0, I'm going to show that u dot u is not 0. Well, I didn't show it's not 0. I showed it's positive. But that's enough. If you ask me to show that a product of two things is not 0, it's okay to show me that it's positive. You could have showed me that it was negative also. Or positive or negative only. Okay, what I'm getting at is I already showed this. So now I must show this. And that's a pretty easy one to show. Let's write down what we want to show. We want to show that if vector u is a 0 vector, that implies that u dot u is just the number 0. Okay, so u dot u, and use a 0 vector, so you have 0, 0, many zeros, dotted with many zeros. And this is going to equal, well, you multiply those numbers, you get 0, plus you multiply those numbers, you get 0, dot, dot, dot. You multiply those numbers, you get 0, you get 0. So A has been proven. There's the proof for A. Now for B, just so we remember, proof for B, we want to show that u dot v is the same as v dot u. That is, dot product commutes. Okay? So u dot v. U, let's say, is u1, u2, up to un. And I define v to be v1, v2, up to vn. You probably should have said that somewhere. Let v be this, let u be that. Okay, well, dot product, you multiply. You get u1, v1, plus, you multiply. u2, v2, plus, and then eventually you multiply. un, vn. Now, remember, each of these are real numbers. There's n of them. Each of these are real numbers. You multiply two real numbers here. Over here you're multiplying two numbers. Over there you're multiplying two numbers. Well, the product of two numbers of two real numbers have the commutative property. That's v1u1 plus that's v2u2 all the way down to that's v sub n u sub n. Well, here's a dot product. Have v1, v2 up to v sub n, v1, v2 up to v sub n, and dotted with the second term, second factor, u1, u2 up to un, u1, u2 up to u sub n. But this is vector v dotted with, that's vector u. So I showed that u dot v is equal to v dot u. Proof B is now complete. Go on to the proof for C. C is u plus v dotted with w. This is supposed to equal to u dot w plus v dot w. Okay, and W will equal to W1, W2, up to Wn, U and V as defined earlier. Okay, so now we have U plus V dotted with W. Well, U is U1, U2, up to UN, plus V, which is V1, V2, up to Vn, and that mess gets dotted with W, which is W1, W2, up to W sub n. Now, until we prove this, we only know how to multiply one vector by one vector. We have our sum of vectors. Well, when you add two vectors, you get a vector. So if I add these two vectors, if I add U and V, I'll have one vector. So when I add them, I have U1 plus V1, U2 plus V2, all the way down to UN plus V sub n. That's one vector. And that one vector is going to be dotted with W1, W2, up to Wn. That is vector W. Now, let's think of U1 plus V1, etc. as one number. So, we have one number, one number, one number, dotted with one number, one number, one number. We can do that. That I can do. I'll multiply those two. I get U1 plus V1 times W1 plus dot. Multiply those two. I get U2 plus V2 times W2 all the way down to here, which will be U sub n plus V sub n Wn. Okay, that's the dot product of this. Now, let's look at each of these things that we are adding. They all have three numbers: addition, multiplication. We could distribute the W1. This is U1 W1 plus V1 W1 plus, over here we distribute W2. We get U2 W2 plus V2 W2 all the way down to U sub n W sub n plus V sub n W sub n. And now I'm adding many numbers. In fact, 2n numbers I'm adding. And the order I add them in is up to me. I want to add that one and then that one, all the way up to that one first. U1 W1 plus U sub 2 W sub 2, all the way down to U sub n W sub n plus, and now I want to add those. I want to add V1 W1, this one, plus that one, V2 W2, all the way down to this one, V sub n W sub n. But really nice things are going to happen here, because in this sum, I'll take the first values, U1, U2, up to U sub n, and I'll dot them with the second ones, W1, W2, up to W sub n. W1, W2, up to W sub n. Let's verify it. Maybe I made a silly mistake. You multiply those two, you really do get U1, W1. Plus, there's the plus, multiply these two, U2, W2. All the way down to plus UN, WN. Got it. Plus, I'll use the first components again. V1, V2, down to V sub n times, dotted with the second, W1, W2, up to Wn. And that's just what the dot product is. Multiply these two, of course you get that. Plus, there's the plus. Multiply these two, get that one. Plus, eventually, plus, you get that. And this is where we are done. Because this vector is u, and I am dotting it with this vector, which is w, plus this vector, which is u, is being dotted with this vector, which is w, which is u dot w plus v dot w. You can put the vector hats if you like. But the bottom line is I showed that this equals to this. And that's all I was supposed to show. That is letter C. Letter D. I want to show the following. That a scalar times vector u dotted with vector v is the same as u dotted with the scalar v, which is the same as c times u dot v. Okay. So let us start with this and show that it equals that. That is, I can move the c between the u and the v. So c times u dotted with v. Well, here is c times u. C, here's u, u1, u2, up to un. That gets dotted with v, which is v1, v2, up to v sub n. So let's clean this up. A scalar multiplies each entry by, in this case, by c. So we get cu1, cu2, all the way down to cun, dotted with v. v1, v2, down to v sub n. Now let's think of those as one number. So we multiply those two, and we get cu1 times v1, plus multiply those two, you get cu2 times v2, all the way down to that product, cu sub n times v sub n. Now, we keep having three numbers to multiply. 1, 2, 3. 1, 2, 3. Those are real numbers. We have their commutative law. Remember, I want to get the c in between their u and the v. So, this is u1 times c times v1 plus u2 times c times v sub 2, all the way down to u sub n c times v sub n. But I also want to get the c with the v. So I'll use their associative law. u1c v1, didn't change the order, but I'll move the parentheses. u2c v2, I could move the parentheses all the way down to u sub n times cv sub n. Okay. Now, u1, u2, up to un. u1, u2, up to u sub n. Dotted with the second component, cv1, cv2, all the way down to cvn. And we can check, maybe we made a mistake. You multiply those two, yep, you get this, plus multiply those two, yep, you get that, all the way down to plus, multiply those two. So that's looking good. So we have u1, u2 up to u sub n, dotted with. Now, since each one of these n numbers have a factor or c, I can factor out the c. This is c times v1, v2 up to v sub n. And remember, it was u dot with this. So what's in this bracket here is this. It's u, that's u, dotted with this. Well, here's my u, and I'm dotting it with that. Well, like I said, this vector is u, and I'm dotting this with what's in the parentheses, in the big brackets, which is c times v. So, if I call this our expression 1 and expression 2, and this expression 3, if I show that, so now, I know that this is valid. I just proved it. Now, so I know that equation 1, expression 1 equals expression 2. If I also show that expression 1 equals the third one, which would be, yeah, if I show that the first one is also equal to the third, so expression 1 is equal to 2, and it equals to 3. These two have to be equal. Okay, if I tell you x is equal to y, and y equals z, how can it not be true that x equals z? Since this is a proof or channel, let us actually prove that. Okay, if x equals y and y equals z. So how can we prove this? How can we prove that? Oh, first let's state the theorem. Then x equals z. Okay, proof. If x equals y, that implies x minus y is 0. And if y equals z, that implies that y minus z is 0. If I add these two, I get x minus z equals 0 and x equals z. So yes, it is true. I mean, I wasn't afraid it wouldn't be true. Okay, so I'm going to show statement 1 equals statement 3. I'll even try to prove it right here. So cu dotted with v, I want to show that this is c times u dot v. The reason I chose that one is I only have to move the brackets. For example, if I can just move the brackets. If I try to show that the second one is equal to c times u dot v, I would have to move this. Okay, it just looks easier to do the one I stated. Okay, so definitions. C times u is cu1, cu2, all the way to cun, dotted with v, which is v1, v2, down to v sub n. And this is equal to, think of these as one entry. This is equal to cu1 v1 plus cu2 v2 all the way down to cun vn. But this is c times u1 v1. See how easy I was able to get the u's and the v's together and to separate the c, un, vn. And now I can factor out the c. So I have u1 v1 plus u2 v2 all the way down to un vn. So here's the c and there's those brackets. Let's write down the n first components, u1, u2, up to un, and I dot that with the second components, v1, v2, down to vn. Close the bracket. Well, there's the c in the front, and this bracket, this is vector u, and I am dotting it with vector v. And I can just write it with smaller brackets, u dot v. But that's what I wanted to show. I wanted to show that this, which equals that, which eventually equals this. So I did show it. That completes this video. If you like to see material like this proven on a daily basis, subscribe to my channel. All we do are math proofs here. Leave a comment. Let me know what videos you would like for me to make up. And most of all, watch and learn.